So welcome everyone for our weekly seminar here at IAFORTH. So today we have the pleasure to have with us Núria Torres Albá, who will give us a talk about the X-ray in the torus, a multi-epoch study of obscuration in nearby Aegean. But let me introduce Núria very quickly. So Dr. Torres Albá is currently a postdoctoral fellow at Clemson University in Clemson, US. She obtained her PhD in 2019 at the University of Barcelona in Spain, and she has been working at the Clemson University ever since. Núria has focused her research on active galactic nuclei and their surrounding across the electromagnetic spectrum. In particular, she has been working on the interplay between star formation and Aegean activity in luminous infrared galaxies, LIRGs, on investigating the quantum-thick Aegean fraction in the local universe, as well as on the modeling of gamma-ray emission produced in the interaction between Aegean and obstacles. And her current research is focused on characterizing the Aegean torus via X-ray observations. Okay, so thanks, Núria, for being with us today. The floor is yours.
Yeah, thank you for having me. So as Karina mentioned, currently I am working on trying to get some tighter constraints on the torus geometry and the distribution of clumps within the torus. And we're trying to do that via using X-ray observations of Aegean. I want to add for people who maybe came in a bit later that I'm going to be visiting in person in Forth in the week of the 5th to the 9th, I think, of June. So if anybody has any interest in speaking, I would obviously be very happy to have discussions. So to start our talk, the first elements that need to be sort of explained are those that pertain to Aegean structure. And more specifically, I am going to be focusing on all of the elements of an Aegean that are actually relevant to the X-ray spectrum. The first thing we need to produce the X-ray spectrum of an Aegean is an accretion disk. We know that there's this accretion disk near the supermassive black hole, and it produces thermal emission in the range between the infrared to the UV range. We also know that this accretion disk cannot be seen from all possible directions, like as what is depicted here. We can see, if we're looking at this Aegean through the torus or through these layers of obscuring material, we're going to be seeing an obscured Aegean in the sense that not all of the light coming from the system gets to us. But if we look through another direction, through an unobscured direction, then we're going to be seeing all of the emission of this Aegean. And in particular, what's producing the X-rays inside the system is the corona. And the corona is just a hot plasma of electrons that is placed somewhere near the accretion disk. We don't know exactly its shape or shape or size or exact location. But we know that in this plasma of hot electrons, the disk photons, these ones from the infrared to the UV range, get upscattered via inverse Compton. And some of them can acquire X-ray energies through this process. The shape of this emission is going to be that of a power law, which is this line I'm showing here in this SCD, this unabsorbed power law on top that eventually has a high energy cutoff. The unabsorbed emission is what we would see through an unobscured direction. But if we're seeing this Aegean through the torus, then we're going to be seeing an absorbed spectrum. And the amount of absorption is going to dictate the shape of the X-ray spectrum. And in here, you can see this initial shape here. The one most to the left is the lowest level of absorption. And when we have the highest possible absorption, which would be the lowest of all curves, the photons, mostly at low energies, have been very, very heavily suppressed to the point that sometimes none of the soft X-ray emission, which is what we would call below 10 keV, can survive the process of exiting the torus, and none of it can reach us. A great thing about this, though, is that the shape of this emission is very heavily dependent on the amount of obscuring column density, what I'm calling NH here, the amount of material in our line of sight, meaning that by studying this shape and trying to model this shape, we can get a very good idea of the amount of material in our line of sight. And why is this important? Well, this is because now we know that the torus is patchy. And we know this thanks to a variety of ways, one of which is just infrared studies that are probing the dust via SED modeling. And another one is via the direct observation of occultation events in X-rays, meaning seeing a spectrum of the same X-ray source at two different epochs and observing that the amount of obscuration in the line of sight has changed. Meaning, if we go back to the first slide, that the shape of the spectrum can go from this very unabsorbed shape to a much more obscured one. And this can happen in timescales as smaller as about a day or less, and as long as years. So this is showing us that the amount of material in our line of sight is changing. It has the capacity to change. And the scales at which this happens can inform us of the distance between this material and the supermassive black hole, which in turn can allow us to place some constraints on the structure and distribution of clouds in the torus. That would be the idea. Here is an example of a simulated spectrum of a source at two different epochs in which there has been a change of column density. The top spectrum, this is the simulated XMM and Nooster spectrum. So the XMM bits would be the darker colors, the red, the dark blue, the Nooster would be the pink and the cyan. And these have been simulated to be simultaneous, each pair, XMM to Nooster, XMM to Nooster. The top spectrum is the least obscured spectrum, and the bottom spectrum is more obscured. And in fact, I'm attaching here as well the confidence contours of the NH, the column density in the line of sight, versus the photon index of the spectrum, meaning the inclination of the original intrinsic AGN power law. And as you can see, these two NH determinations taken from fitting this spectra via our X-ray models are incompatible with each other at the 3 sigma level, meaning we can distinguish very well that there has been a change in NH if we have a spectrum such as this that has changed with a certain distance, with a certain time scale. However, so far I've only talked about this one component of the X-ray spectrum, which is this intrinsic emission coming from the corona that has to cross all of the torus. And in this process, a great part of it can be lost, particularly at higher column densities and particularly at lower X-ray energies. This is what we call the line of sight component or transmitted component that manages to go through the material of the torus. However, there is also a very prominent component, an additional component to the X-ray spectrum of an AGN, and this is what we call the reprocessed or reflected component. Reflected is actually the name that is most commonly used. It's perhaps not the best name for people outside of the field because this is not reflection in the sense that the photon just collides with something and gets out there with, the same inclination angle, same energy unchanged. This is actually Compton scattering, meaning in this process of going through the torus, the photons can collide via inverse Compton scattering with the material of the torus, sorry, not inverse Compton, normal Compton scattering with the material of the torus and change direction and change energy, get down scattered to lower energies. The good thing about this reprocessed or reflected component is that everything that gets into our line of sight may be coming scattered from all parts of the torus. Like if you look at this drawing here, the corona is emitting in all possible directions. And from all possible directions, we may get a collision that brings the photon back into our line of sight. Meaning the shape of the reprocessed component depends on the average geometry of all of the material in the torus that is doing this reflection, which is potentially, or assumedly, at least so far, the whole of the torus. So studying the exact shape of this reflected component can give us information on the shape of the overall shape, average shape of the torus. And in here, I am showing the resulting X-ray spectrum with what will be all of its components. We have this main power law, which in this case is unobscured, and this is coming from the corona. If this is obscured, then the part at lower energy is going to be very heavily suppressed. We also have the reflection hump, which is this reflected reprocessed component, and very intense iron lines, which also come from this reflection and are very often used as a powerful diagnostic for the presence of an AGN in a system. Something else that we may have there that generally pollutes the study that I'm going to be talking about today is a soft excess. And this can be coming from reflection from warm material. When I say warm, I mean significantly ionized. The reflection hump is coming from cold material, so mostly not ionized material, at scales supposedly of the torus. And the soft excess could also be coming from a bunch of other processes in the host galaxy, for example, such as anything that can cause hot gas. And this can be thermal emission coming from processes such as star formation, for example. What is interesting to us, though, let me go back and emphasize, is this reflection component. Because the reflection component, as I said before, depends heavily on the structure of the reflecting material. And in here, I am showing how the shape of the reflection component, this is only the reflection component, changes in the spectrum as a function of different parameters of the torus. For example, the covering factor. If the torus or the reflecting material is a very flat, geometrically thin disk, the shape of the spectrum is going to have a much different shape. While if the torus is very thick, physically thick, we're going to have a different shape of the emission. The same happens with the inclination angle through which we are looking at this torus. And interestingly for us today in particular, of the average torus column density. So this, in this case, is not going to give us the line of sight column density like the transmitted component was doing. This is giving us the average density of all of the material that is reflecting, the average density of the torus. And finally, the metallicity can also have an impact on the shape of this spectrum. As you can see, however, all of these shapes can have important degeneracies, particularly in the soft energy band. And in here, I've marked this line, these vertical lines at 10 keV. Above that, the only way we can actually fit this spectrum relatively well nowadays is by using Nuster. Meaning if we actually want to say something about the shape of this emission, of the reflection continuum, we need Nuster observations because they can allow us to break degeneracies between parameter shapes, the influence of different parameters into the shape of the AGN. So in here, I am just recapping. When we have a patchy torus, we can imagine that it's going to be turning. And in this process of turning, we're going to be probing different lines of sight. So in this process, we may see the transmitted component or the intrinsic original power law, which is here in blue, being heavily suppressed as the material, the amount of material in our line of sight increases. However, the reflection component is not really expected to change at these timescales. And this is because it's coming from material that is much larger scales, physically speaking, and you would need a very long time for this material to change its shape and properties significantly enough to affect the shape of the reflection continuum. So for the study that I'm going to be talking about today, in which I am involving multi-epoch observations of AGN in a maximum span of some 20 years, we will consider that the transmitted power law changes its shape because at different epochs, we may be piercing different sides of the torus. However, the shape of the reflection continuum is not really expected to change. And let me just note that in this spectrum, I also have some thermal emission and this scattering component that is here, which would just be elastic collisions of the photons coming from the corona that managed to sort of cross the torus without having their energy significantly affected. And so it has this same shape as the intrinsic original power law, but much, much lower normalization, 1%, 0.1% of the original intrinsic power law. So why is it so important or so relevant to us that we can model both of these things, right? We can use the shape of the transmitted component to model the amount of material in our line of sight, but at the same time, we can use the shape of the reflection continuum to model the average density of the torus. And it is interesting because this gives us a further clue into the structure of the patchy torus. These are some results that we published last year, in which I am plotting for a sample of Compton-thick AGN candidates. And when I say Compton-thick, this refers to an NH in the line of sight that is higher than 10 to the 24 per centimeter square, meaning very optically thick sources. I'm plotting their obscuration in the line of sight in this vertical axis versus the average density of the torus. So if this torus were to be homogeneous, you would expect all of the data points to fall in this diagonal brown line. However, as you can see in this plot, the majority of this plot of these sources fall very far away from the one-to-one relation, meaning through all of these sources, we're piercing through either an overdense or an underdense region of the torus. Something that one could expect, however, is if we model this line of sight NH at different epochs, would these data points then move vertically up and down through this plot? And I say vertically because the average NH of the torus, as I said, this is a property that's coming from much larger scales, and this would change at much larger time scales that we likely are incapable of probing right now. So that's a possibility that these data points would go up and down around the average density of the torus. However, this is further proof that what we're seeing in the AGN is a more complex structure than just an homogeneous medium. The motivation, though, overall behind this work is, what if by exploring the changes in an age in the line of sight at different epochs and at which typical timescales this happen, are we capable of placing tighter constraints on the cloud distribution of this torus, like characteristic cloud sizes, cloud densities, and distances to the supermassive black hole? And this is motivated by the existence of interesting findings in previous works. For example, there's a work by Maiolino et al. In 2010, in which they see cometary tails in broadline region clouds that are intercepting our view of the torus. And they know this because as they observe an obscuring event or an eclipsing event, they see suddenly a very sharp drop of emission, so a very sharp increase of column density that then recovers very slowly. So they interpret this as the fact that these clouds are orbiting so fast that in the direction of movement, there's shocked material as it moves quickly through the ISM, and therefore a much higher density compared to the other direction, in which they have a sort of leeway to decrease their density profile very slowly. An example of one of the ways in which one can use the profiles of an eclipsing event to place constraints on the tops, on the clouds, is by this paper by Markowitz et al. In 2014, which I am showing a plot of here. In the top panel, what you see is just a flux ratio between high and soft energies. So you can see that the ratio of emission coming from high energies and soft energies is changing. And this gets translated into a change of column density in the line of sight. The three lower panels are the same data-wise, but the model placed onto them is different. The first panel is assuming that we're fitting this with a single spherical cloud. The second one, I believe, is two different clouds, one passing after the other. And the final one fits the data by assuming a shell of material, meaning the outsides of this ball or of cloud are much denser than the inside. It's sort of empty inside. And so by fitting these data profiles, we can get some idea of the shape, the exact shape and distribution density of the material that's obscuring us. Something else that is interesting is that other works have found some peculiar results. For example, Laha et al. In 2020, in a sample of some 20 Cipher2s, saw that only 7 showed variability in obscuring column density. The reason or the question here is, why does this happen? If the torus is patchy, how come not all of the galaxies are changing in age with time, right? So we're expecting that all of your obscuration is coming from a cloud distribution. They should be changing with time. And we do not exactly see that in the majority of galaxies, according to some surveys. The majority of studies, however, are focusing on an age variability of single sources and mostly selected to be heavily in age variable, so particularly interesting sources. So we are currently lacking extensive studies, such as the one I mentioned of 20 galaxies, that are giving us a much broader view of how common these events are in AGN, and therefore how common this patchy torus of different eclipses is in nearby AGN. In fact, the most extensive study that can be used for calibration nowadays is the study of Markowitz 2014. And they did continuous monitoring over, I think, 16 years of 8 different objects, 17 years, I actually have it here. And they only saw 12 eclipsing events. This is what I am showing here. 12 eclipsing events in total. The upper plot has 8, the lower plot for type 2 AGN has 4 individual events. And this is being used to calibrate current clumpy models, at least in X-rays. So this plot is just showing the probability density of seeing an eclipsing event at different timescales. And as you can see, not all timescales are being probed in both types of sources. And we are calibrating and assuming that we need to fit this probability density that may be heavily biased because we only have 4 individual events to calibrate it with. Still, it is the best thing that we have so far. So obviously try to fit it. So there is a need, I believe, in the community to increase our knowledge of how typical, how common these eclipsing events are and at what characteristic timescales they happen and what is the characteristic change in an age at different epochs. So my objective for this work is to determine the changes of obscuration in the line of sight at different epochs for a sample of AGN by studying this transmitted component, again, that I'm showing here, of different observations. And at the same time, constrain the torus geometry, so whether the torus is thick or thin, the inclination angle, the average torus density, via the study of this reflection component that I'm expecting does not change in these short timescales. But in order to do that, we need to select an ideal sample that allows us to study both components. And that is because if you go back to the plot, if we're looking at a case at very high NH, which is what we're going toward now, you will see that the transmitted power is completely suppressed. We don't see it, we only see reflection. If that happens, small changes in the obscuration are not going to be perceived by us. We're only seeing the reflection component, so we cannot constrain this NH variability. On the other hand, if we're looking at a very unobscured source, all of the transmitted power law is practically not suppressed. And this can be an order or 2 orders of magnitude brighter than the reflection component. And then we cannot constrain the reflection because it barely contributes to the overall emission of the AGN. So what we need is a sample of highly obscured, but not quite Compton thick AGN, meaning with densities between 10 to the 23 and 10 to the 24 per centimeter square, column densities. So in order to do that, we perform a search selection. A collaborator of ours who was also a student at Clemson some time ago, he studied a sample of 100 local VAT detected Compton thin AGN. The VAT detection is interesting to us because anything detected by VAT in this high energy range has to be very, very bright. VAT is not extremely sensitive. So this is making us select local bright AGN, which are ideal to have a large number of towns in our spectrum for the complex study that we want to perform. And again, that they have to be in this sort of sweet spot of column density in the line of sight. To derive Torus properties, what should resolve it was get at least, or force that sources that he wanted to study had at least 1 Nooster observation and 1 soft X-ray spectrum. And he was taking this data from the archive. And as he was taking this data from the archive, they were not necessarily simultaneous. This in here is an example of one of such sources. The XMM spectrum is in red, the Nuster spectrum is in blue. And as you can see, they don't match at all in the energy range in which there should be overlapping. Meaning, in this particular case, there has been some variability. This is because observations were not simultaneous, right? So actually what he saw is that out of these 100 or so sources that he analyzed, he had to consider some form of variability, spectral variability, in 31 of them. And this variability he had to consider was sometimes in obscuration in the line of sight, which is the one case I'm showing here. As you can see, the two different observations have a different estimate for the obscuration in the line of sight. Or sometimes the variability he had to ask for was in intrinsic flux, sometimes both actually. So intrinsic flux, just meaning that the original power law has changed to normalization, right? The AGN is just throwing out more photons. And out of these 31 sources that I considered to be very interesting because they were all potentially variable in an age, I believe that when you're just analyzing two different spectra, which is the case that I'm showing here, sometimes you do not have enough information to really be certain if what you're seeing is variability in line of sight NH or in intrinsic flux. Sometimes they can be very difficult to disentangle, particularly if the data quality is not excellent. So I considered all of these sources as also possibly NH variable sources, this 31 source sample. And out of these 31 sources, there were 18 in the archive that had more than the two observations Shuri Zhao had analyzed. And that was interesting to me because I was not going to repeat exactly his same analysis. I wanted sources that had more observations that could perhaps help us break the degeneracy between NH variability or intrinsic flux variability. So this 18 source sample would be the starting point of this study. And how do we perform our analysis? Well, we simultaneously fit all of the observations for each individual source with self-consistent torus models. This would be my torus, Borus, UX, Clampy. What these do is they just force the lines component, the iron lines component in the reflection continuum to be self-consistent, which is not the case with what we call phenomenological models, which would be adding a Gaussian and the reflection continuum separately. So in here, I'm showing one of the examples of one of the sources in the sample that has three different observations. The two in black and blue are from XMM, and the one in gray is from Nuster. And in here, it's a bit hard to see, but there's a dotted lines, and the three dotted lines that are slightly different. These dotted lines are the transmitted component. So the original intrinsic power law that has been obscured. And from here, we can get an idea of the NH of the line on in the line of sight. In fact, as you can see, the three spectra show slightly different curvature in this lower energy range. And this is very indicative of the presence of NH variability. But at the same time, we're also considering the fact that there may be some flux variability, intrinsic luminosity variability, and this will affect us mostly at the higher energies. And then the shape of the reflection component, as I've said a few times, we consider that it's constant. And here I am showing it in these dashed lines. The fact that I'm imposing this to be constant helps us very, very much to constrain the parameters of the reflection, because the same shape of the reflection component is now forced to explain three different spectra that have three different shapes, right? So the same shape of the reflection, you added three different shapes of transmitted power law, and these need to match the three different spectra. And this has been shown by this work of Marchesi et al. To heavily improve the constraints of the torus parameters. And here I'm showing his confidence contours for the inclination angle through which we're seeing this AGN, and the average column density of the torus. And as you can see, he had three different observation epochs, and in some of them, he had very, very large errors. However, when you put all of them together, you get something that's compatible with all of them at the 3 sigma level, but has much, much lighter constraints. So our objective is to also improve the constraints on the torus geometry so that we can correlate any NH variability properties we find to the torus geometry parameters. And so far, we've been working steadily in this work. It's a rather complex and mostly long fitting effort. But we've analyzed a pilot project that was published by one of my students on a particularly interesting galaxy. And I also have just submitted a paper on 12 sources, and these are the results I am mostly going to discuss now. We also have a monitoring campaign going on a particularly bright, interesting source, and in-depth analysis of more complex sources by another one of our students. But in total, we've so far analyzed more than 100 different observations. And here I am showing some of the results that we derive from this 12 source sample. And what we found is that in the variability analysis, turns out that 5 sources are compatible with not being variable. So if we look at the non-variable case, which is the plot in the top right, I am plotting NH as a function of time in days. The 0 is the time of the initial observation, whenever the initial observation was taken, and at the end is when the final observation available for this source in the archive was taken. So the data points that you're seeing here are the NH in the line of sight, the obscuration in H at different epochs. And the dashed lines are the average torus NH that, as I said before, we don't expect to change in these timescales, derived by 2 different models. And the shaded areas are just the error range of this average torus density, which in some cases, as you can see, is pretty large, but in some cases it's much better constrained. So a non-variable source, such as this one, as you can see, we have 4 different observations, but all of them are compatible with having the same value. This is a non-variable source. 5 of our sources turned out to be non-variable. However, other 5 sources look quite a lot more like this, like NGC 4388. And as you can see, it goes up and down very much in NH. Other sources behave a bit like this one over here, IC4518A, in which I labeled it undetermined, right? 2 out of 12 sources are undetermined. And this means that their spectral variability can be explained equally well by assuming just NH variability or just intrinsic flux variability. So I cannot be sure that these sources are NH variable. It's interesting to note, however, just from a starting point, that this is a sample that I purposefully biased toward trying to find NH variability. And even then, only 5 out of 12 surfaces, less than half, turned out to be clearly NH variable. Meaning that, again, we face this issue that we have Apache torus, but we're not always seeing NH variability. And it is unclear if the current structure torus models or simulations would be able to reproduce these results by assuming Apache torus. Something else that is interesting and may have been noticed already by some people is that if you look at these 2 plots down here, the average density of the torus is sometimes very different from the density in the line of sight, even if you consider all multiple epochs. This is quite interesting because initially when I showed that plot of NH in the line of sight versus average NH of the torus, I was expecting that by taking observations at different epochs, they would oscillate up and down around this best fit value of the average torus NH. This doesn't happen. In fact, for 8 out of 12 sources, the 2 determinations are very far from each other. 7 of them look quite like NGC 4388, and 1 of them, but also the source that was published individually by Pizzetti et al. 2022, behave a bit like this one, in which the reflection material is much, much denser than the obscuring material. And again, in 7 sources, we have the opposite scenario. The obscuring material is much, much denser than whatever is causing the reflection, which is something that surprised us initially. And this discrepancy can be of a factor between 2 or as high as 200. Like notice, please, that this plot here, the indeterminate source, is in log scale so that everything could fit in the plot. So this may be suggesting a physical disconnect between the obscurer and the reflector. Whatever is causing the obscuration and the reflection may not be the same material as was originally thought. Oops. Possible explanations for what we're seeing. I would say it's easier to explain the case in which we have a much denser reflector and a much thinner, optically always, thinner obscurer. And this may be due to the fact that we may have an additional ring or flattening of material close to the central black hole that is causing this reflection, very thick material, but we are not piercing it. We're looking through a line of sight that is not intercepting this reflection thick material, meaning possibly we're looking through this very broad cloud distribution, but we have this thin ring, horizontal thin ring of material that's causing reflection, and we're actually not piercing it with our line of sight. And in fact, one of the models that we used, it actually requires the addition of this component in order to be capable to explain the shape of the reflected emission. And it does require it for these two sources in which we see this behavior. So in this sense, the results are sort of self-consistent. And this inner ring of thick material has been interpreted to be maybe a warped accretion disk. Something that may be a little harder to explain is a scenario like this one. So 7 out of all of our 12 sources will actually have a much thicker obscurer than the reflector. So we know that there's no this thick material near the central black hole that is causing reflection. However, if we have a cloud distribution that's causing the obscuration, and it's actually a relatively thick cloud distribution, why are these clouds not reflecting? They are there. So one would expect that they both obscure and reflect. But what we're seeing is that the reflection is a very, very thin thing. A possibility to explain this would be that, in fact, the torus is, again, more complex, and we may be having multiple reflectors. And this is something that has been proposed, I believe, to explain infrared SEDs, a multi-phase medium in which we have a sort of widely distributed thin ambient medium that's taking up most of the space. And in this medium, there's also individual thicker clouds. This thin medium would be acting as a thin reflector, and the cloud distribution would be acting as this thick obscurer. These two distributions should obviously overlap. However, these dense clouds, if they are there, they should also be reflecting. And it's possible that they are doing so, but in my models, I am only imposing that there's one reflector. So if you look at this spectrum here, and this is just a toy model, I've just added it, it's not fitting anything, but it has a variety of different components. Usually I would only consider a line of sight component, so the intrinsic power law that has been obscured, and one reflection component. And this is because we have already so many parameters and so many components, we cannot expect to actually disentangle even more contributions. But perhaps there's also a thick reflector in there whose contribution gets sort of diluted between the multiple components that we're introducing. In fact, what I'm showing here in red is the transmitted power law. So this is an obscured intrinsic power law with a Compton thick obscurer. And in cyan would be the thin reflector. So it would be a scenario similar to what we're seeing here, right? If these clouds are also reflecting, we would add a new component, which is this dark blue component. And as you can see, when we put the three together, it is possible that this cyan line, this reflection component, is favored by our modeling because it's more prominent in this range at lower energy, at between 2 and 5 keV, where there is nothing else that can contribute to the emission. So this component becomes prominent to compensate for that, while the blue one gets sort of absorbed into the contribution of the two different components, the red one and the cyan one. I think this is a possibility that is worth exploring when we have very, very good data quality. However, if I go back to more general sample results, in here I am plotting average properties of the variable sources and the non-variable sources, always in NH variable, non-NH variable, of the sources in the sample. Before I go into it, just a disclaimer, there's 5 sources in each bin, 5 sources are variable, 5 are non-variable, 5 are variable, and 2 are undetermined. So don't even look at the bin in the middle. And in the other 2, even though we may see some marginal hints, none of these results are significant enough to claim any huge differences between the variable and non-variable sources. However, the hints that we're sort of seeing, and here I am plotting the timed average line of sight NH for the different source populations. And this would mean, so if we go back to the source, this would be a value that is like around 40 for this source. So the average of all of these different piercings of the torus. And as you can see here, non-variable sources, non-NH variable sources, tend to have thinner tori, while variable sources tend to have optically thicker tori, so more obscured. The density, the average density of the obscurer in variable sources seems to be a bit higher. And then if we consider the difference between the density, this average density of the obscurer, and the average density of the reflector, this also seems to be a bit higher for variable sources. So what this means is, going back to my original different showing plots, non-variable sources tend to behave like this, meaning their NH in the line of sight tends to be more compatible with the average NH of the torus. And variable sources tend to behave like this. This could make sense in the sense that non-variable sources may be sources in which we're just piercing through a very edge-on scenario in which all of the obscuration is dominated by the reflector, by a thinner distribution that's more homogeneous, perhaps. And finally, the cloud dispersion, so whether these clouds are very close together or very spread out, seems to be, again, larger in variable sources. Again, however, I repeat, we only have 5 sources in each bin, so our current priority is to increase the sample size to make sure that what we're seeing, that these trends are actually maintained, or whether they actually completely dissolve and there's actually no significant difference between torus properties or torus geometry of variable and non-variable sources. Something else that is interesting that can be done by using the data of the sample is plotting the variability of NH in the line of sight as a function of the timescale of this variability, meaning I'm plotting here the difference in line of sight NH, the difference in obscuration of 2 consecutive observations and the time span between these 2 observations. And as you can see, I only see large differences in obscuration with very large times. This could be interpreted as perhaps the variability is coming indeed from large scales, as in scales of the torus, because anything between 0 and 1 and 10 days would have to necessarily come from the broadline region. So we mostly see no variability or very little variability in these timescales, and we see very large variability at much larger timescales. So we need to wait much longer times to actually see significant changes in NH. And hopefully, once we populate this plot even more, because right now we could be seeing this difference simply because we don't have enough sampling of the smaller timescales. Once we populate this, our hope is to be able to contrast and compare this against simulations of cloud distributions. Just put the cloud distribution there, just make it move, take random directions in there, and see if we actually manage to reproduce the data by simulating one generic patchy torus. This is all, however, future work. And I'll leave you here with some of my conclusions. As I said, only 5 of our 12 sources turned out to be NH variable, which I believe is surprising in a sample that I purposefully biased to be variable. The results so far may be hinting at a physical separation between the obscurer and the reflector, because the materials do not tend to have the same density. In most cases, the material that is responsible for reflection is thinner than the obscurer, but we know that we have a big limitation in our study, actually 2, I would say. The first one is the lack of constant monitoring. We cannot choose our timescales. We're using archival observations and we have what we have. And even if I would like to have a lot of observations probing the timescales between 1 and 10 days, I cannot choose to have that. This is all coming from the archive, and it's actually quite time-consuming and complex to get proposals passed for monitoring, searching for NH variability. Another problem that we have right now is that all of these results that I've been telling you about they suffer from very poor statistics, as in we only have 12 sources in this initial sample. So our biggest priority right now is to increase the sample size to confirm or disprove what we've seen so far. And actually, one of my students here at Clemson is already working on doubling the sample with 12 additional sources. Another one of my students is developing a method to quickly find variable sources or potentially variable sources based on quick hardness ratio analysis. And the paper is going to be submitted soon. And I have other students working on an in-depth study of particularly interesting objects and some monitoring campaigns going as well. So I will leave it here. And if anybody has any questions, then please feel free.
Thank you very much, Núria. Very nice talk. So let's see if somebody has any question. Yes, Vasilis. Go ahead.
Yeah, I will try to ask first and then leave. Núria, very nice talk. I was wondering, I'm sure you know, there were discussions as early as probably more than 10 years ago using mid-infrared absorption measurements, like the silicate absorption, for example, by Goulding and Alexander. There was this model where they were arguing that the nuclear absorption that we observe in the mid-infrared were actually coming from the disk rather than from optically thick clouds very close to the observer, very close to the AGN, to the emitting source. Have you looked, for example, to cross-check some of your measurements with existing spectra? Spitzer IRS spectra, or even better, have you put a JWST proposal which was accepted?
I have not put a JWST proposal which was accepted.
You need to talk to Tanya.
Nice.
He's
an
expert.
I will. But definitely something that I'd be very interested in is being able to contrast these results with infrared measurements, because it's the only other way we have sort of into the torus, right? And being able to see if what we are seeing is reflected in the infrared measurements, or if there's an absolute, disconnect, as has happened with other measurements, such as covering factor and other things coming from infrared and X-rays. So this is actually a very good point, and something I would like to discuss with you guys when
I haven't followed. Maybe Tanya can comment on it, right? But I remember, the first few years after they published that, personally, I wasn't very convinced. I don't know what the community says now. Tanya, I don't know. You have something else to say?
Tanya?
Hi. Hi, Núria.
Hi.
Sorry, first of all, for missing the first part of the talk. I wanted to ask a couple of questions. Well, the second was related to what Vasilis asked already, but the first, maybe it's a stupid question, is because I missed the first part of the talk. So, excuse me. So I missed how you were making the connection between the reflector and the torus itself, like the emission that you see in X-rays that you attribute to the emission of the reflector, and the fact that that is associated to an obscuration. I joined just after that.
I see. I think this plot is actually maybe a necessary bit for them. So when we are talking about the obscurer is something that is exactly in our line of sight.
Yeah.
So as our torus rotates, the obscurer changes, right? Because we're not. So I mean, the general material that obscures is a distribution, but the exact obscurer at that moment is changing, because you're piercing through a different line of sight into the torus. But this reflected component is coming from everywhere. So this is photons that are coming from the corona in all directions, and they collide with cold material in the torus and get reflected back to us. So the shape of this material is representative of average properties of the whole torus, or of the whole thing that is reflecting, which may not be the torus.
and how you connect it to the obscuration itself, because you see it in emission, like reflection, right?
Yeah.
From
So
the torus. How do you make the connection to the absorption?
The best maybe is this. So these are two different components, right? When we do our fitting, we fitting two components simultaneously, and the sum up of these two need to explain the resulting spectrum. Right, in here, the resulting spectrum would be the black line. Right, and the contribution of both the transmitted power law, which depends only in our line of sight at a given moment, and the reflection component, which we expect doesn't change significantly between observations. The sum of these two components needs to be representative of the overall spectrum, right? So if you go to the actual spectrum that I have in the talk, this, perhaps this is easier to see. In here, the solid line is the overall best fit.
Yeah, okay.
The dotted line is the line of sight component from which I am taking the line of sight NH. And the dashed line is the reflection component from which I am taking the average properties of the torus. So as you see, the two of them sum up to be this overall best fit line.
So the NH of the line of sight, you get it from the hard X-rays, and the NH of the torus from soft?
It's not exactly that. Both components can contribute at both different ranges.
Okay.
But if you have both ranges, you can disentangle much better between degeneracies, between the two different things, right?
Okay.
Yeah, but the average NH of the torus is what's shaping this dashed component here.
Okay, so you are obscuring two intrinsically different emissions. That's how you...
Yes and no. I am obscuring definitely the line of sight component. That is pure obscuration. The reflection component is coming from that, yes and no. So these are shapes of reflection component, of reflection spectrum, right? And this is coming from the original power law that spread out in all directions and collided with electrons everywhere via Compton scattering and got down scattered into X-rays. And two things happen here. If this NH, maybe the average torus NH, which is the lower plot, lower left, is the easiest for this. If the NH of the average NH of the torus is very high, you'll get more reflection. So this component is more prominent. So this is the red here. But at the same time, it's less prominent at softer. Because it gets self-absorbed.
Yeah.
And the blue one, see, is exactly the opposite. So this is how we get this average NH of the torus.
Okay. Okay. Now I think I get it. So a follow-up question related to what Vasilis was asking: is there in any way you can make a connection with the modeling that it's done in the mid-infrared with I'm sure you are aware of models from Nankova, Stalesky, Honing, and all these people, right?
Yes.
Is there any way in which the characterization of the torus in the mid-infrared, the properties that can be derived from these models, can be useful somehow to be able to make a connection with either with the average torus NH or some spectral...
Yeah, we would honestly like to explore that more. We've been trying to find different ways in which one could make a connection, maybe SCD fitting, maybe, because this is also supposed to give you, global torus properties. We're not sure, however, if what is dominating the X-ray emission and what is dominating the infrared is coming from the same exact scales. So there's always the possibility we're not going to see a correlation, but then that would also be a result, right? It's not coming from the same scales. So we're definitely interested in exploring more and more a possible connection to other wavelengths. And as you were saying, the mid-infrared would be the ideal one, which is something that, again, I'm looking forward to maybe discussing and getting more ideas once I am there.
No, definitely. I mean, this is something that with JW we can get to the sub 100 parsec scales, right? To do, it's not. I don't think the torus is resolved. It's not possible to resolve the torus, not even for the closest safer galaxies. I think in hot dust at least.
Yeah.
But I mean, we can make sure that we are looking at it with minimal contribution from the host galaxy, right? And
Else,
I think
yes.
that's at least something that we can control and disentangle.
Yeah. Yeah, and I think it'd be very interesting to see if we really recover this difference between an H variable and H non-variable sources when we're looking in the infrared. Like, do these two source populations truly have different properties? Do they behave differently in any way, or not?
No, yes.
That would be indeed very interesting to.
Super interesting. Okay, it will be very nice when you visit in a month or so, I think. Yes.
We have a plan.
Yes.
Perfect. I see another question, Elias?
Yes, Elias.
Yes. Hi, Núria.
Hi.
Congratulations for your talk. So I have two questions. The first is regarding what Tanya mentioned about the two different NHs. So my understanding is that essentially the second NH of the reflection is something like a tracer of the average NH in the torus.
Yes.
And the first one is what happened with the density across the line or according the light of sight, right? Along the light of sight.
At the exact moment that we observed.
Okay. And the second one is about metallicity. I would like to ask you, how do you measure the metallicity? Do you have optical spectra?
Yeah.
First of all, this is the gas phase metallicity? Okay, and do you have optical spectra?
No, we don't. So the metallicity, the way we measure this obscuration, we're talking about NH, which is the hydrogen column density. This is actually an equivalent measurement. So this would be the amount of hydrogen atoms we would have in our line of sight if everything in our line of sight was hydrogen. However, not everything in our line of sight is hydrogen. We do know that. And it is difficult to know how much contribution is coming from other material, which is why we talk about this equivalent density, because in the end, it just means how many electrons you have in our line of sight. And that's what's causing obscuration and what's causing scattering away from our line of sight. The metallicity, the way it can affect the spectrum is by, the easiest way is affected by the iron, the iron abundance. So in here, what you're seeing in the final plot, the bottom right, what we see here is what we call the Compton edge. And this is just absorption, photoelectric absorption by iron, which can be very, very, very prominent because it has right here a fluorescent line. So the more iron we have, as the metallicity increases, we'll have a very prominent iron lines, we'll have a strong Compton edge and so on. However, with our data quality, it is very difficult to actually see these differences in our spectrum. Like if in here, it looks very nice, no? But if I go back to my real data, and you see here, yeah, indeed, it does go down. But, between a little bit and a lot, there's a lot of scatter in this area. So what we do is we generally assume solar metallicity. We know that's not exactly the case, but it's also true that we can always fit our data with assuming solar metallicity. Something that will be helpful in that regard would be CRISM, which is supposed to launch, I don't know, like in a week or something. And that would actually see this area with incredibly high resolution. And perhaps then we can actually see or determine real properties of the metallicity of this particular material, right? Because it's not even the metallicity of the whole galaxy. is the metallicity of whatever is causing your reflection, meaning the metallicity of the torus, right, of your reflector.
Yes.
So to answer your
Okay,
question, we're assuming solar metallicity. We don't have the data.
So this plot here shows simulation, or is a simulation study,
Yes.
right?
Exactly.
Yeah.
These are
Okay.
simulations using reflection models with a given geometry and seeing, okay, what happens if I make my photons go through this?
Okay.
Yeah.
Okay. It would be interesting to see the results of the coming mission.
Absolutely. And I think we're going to be seeing some studies of this Iron Line and Compton Edge area.
Okay. Thank you very much.
Any other question? Núria, I may also have a question.
Sure.
Have you thought about complementing your studies with radio data, for example? So I'm thinking, for example, about performing this type of study in some radio loud misaligned AGN, where we see clearly the emission from the 2-jet, but we also have, in some sources, we clearly see that, we clearly have that we see a gap in the radio map around the central region, mostly at centimeter wavelengths due to free from because of the torus.
I see.
And there are also studies that basically estimate then the NH from that, and they compare then from values from X-rays studies, for example. So it may be interesting. It could be, I don't know, if there are some sources, I have one in mind, for example, that is NGC 1052. And that is quite prominent, this gap. So you may investigate, for example, how the radio map change in correspondence of your change in the X-ray spectrum. This may help you distinguishing actually if it's the change in the spectrum is due to NH variability or some intrinsic flux variability in principle.
Yeah. I think that's good, and that's not something we had really thought about. Actually, some of the sources in this 12-source sample are radio prominent, and I know this because they're called 3C something, 4C something, so that's sort of giveaway that there's something in there. And in fact, some of them, I'm sure they have even some diffuse, or this one I see, whatever. They have some diffuse jet emission even in X-rays, some of these, that we actually had to, try to get away from our spectrum as much as possible. So yeah, I think it's worth definitely searching the literature for radio observations of these sources to see if there's anything there, or trying to target a source in which this has been done. Yeah, thank you for the suggestion.
Okay, I don't see any other hand up. So thanks again. Thank you very much.
Thank you for having me.
Stop the recording here.
Perfect.